Thank you. Appreciate that. Okay, so last week we started talking about plans and profiles for roadways. We're going to continue on talking about that. Last week we kind of focused a little bit more on the horizontal aspect. We did touch on the vertical. This week, I'd like to touch on the vertical a bit more. A few things I do want to talk about here. So a lot of this lecture that was put together prior is a lot of repeat from last week, so I'm not really going to go over it unless anybody has any questions. We talked about layouts used to provide line, grade, horizontal, and vertical locations of proposed roadways and or structures. Quick plan view of a roadway. This would be as if you were, like say, in an airplane looking straight down. This is all horizontal information. We talk about the vertical portion, which is the profile. This would be as if you took the center line of that roadway, cut down it, and flipped it up on its side, and you're looking more at an elevation standpoint. In the case of this example here, the hard to see green line would be the existing ground, how it is currently along that center line profile. And then the purple lines would be the proposed vertical portion of where that road's going to go. We also touched on last week cross sections. So that is a vertical plane like the profile. The profile is going along the alignment. A cross section is perpendicular to the alignment. We call them typical sections because it's kind of, this is the design of the road, how it's going to go throughout the whole entire length of whatever this roadway is. We'll look at this here in just a second. That's kind of more what I want to focus on. Here's a typical section for a roadway plan. I think I touched on this a little bit last week. Talk about it a little bit more. This is half of a roadway. Far left side starting is the center line, how the roadway is to be built, graded out to the right of way typically, and then how it's going to be graded to meet existing, whether it's in a cut or fill area. Probably expansion joint, see note below. I would say if that is rebar, that would be for a concrete road. Yeah, yeah. Otherwise, I mean, asphalt, they just pour asphalt and it goes and it cracks, and then you got the little tar snakes when they patch it. Um, we'll talk about this a little bit more. Things you do pay attention to within this typical section. We used to have to hand calculate all this information out, starting from the center line elevation that's given on the profile view. From there, we would figure out, okay, say back a curb, for example, how much higher or lower from the center line is the top of curb, and actually calculate the elevation at this point. We have a grade 1 inch per foot for 6 feet, calculate the grade here. We have a sidewalk, a 1/4 inch per foot, calculate this grade. Then for 1 more foot, go 3/4 of an inch per foot, calculate this grade, and then go to, in this case, a 2-to-1 slope, either up or down till you hit existing ground, depending on whether you're cut or fill. So say, for example, this proposed roadway is underneath what is existing ground. At the time, they're going to have to cut through this. Once they hit the right of way, they would go at this 2-to-1 slope until they daylight for a cut situation. They're building this road over the existing ground. It would then be a fill situation, and they would go down at that 2-to-1 slope until they hit existing ground. A lot of times you will see a slope mentioned on the pavement itself. What's the pavement doing? This example here looks like your center line is a lot higher than your edge of pavement or face of your curb. This would be the same on both sides of the road. That's something else I guess I should say. Take this and mirror it, and this would be the whole roadway corridor from right of way to right of way. They're just showing you half of it for simplicity. Some typical sections, though, you will see what is the slope supposed to be from the center line to the face of curb or edge of pavement. It would probably be listed as something like a 1/4 inch per foot, 1 inch per foot, or whatever. I'm probably going to come back to this when we start another slide or two and talk about some other things. I'm going to just kind of go over this real quick. We talked about this last week a little bit more in detail. Coordinates. The hybrid coordinate system is station offset and elevation. Your stationing increases from the beginning to the end of the project. Your offset is then kind of determined on which direction your stationing is going. As you are standing, say, towards the beginning and you are looking up station, where the station's increasing, offsets to the right of the alignment would be usually noted as either right or positive. Any offsets to the left of your alignment would be listed as either left or negative. The positive and negative are probably more of the key things to keep in mind. So as you're standing on the alignment, looking up station, stations are increasing ahead of you. Offset to the right would be considered positive, offset to the left would be considered negative. And then elevations are elevations. So I wasn't going to really hound on this a lot more since we talked about it a bit last week, but if you have any questions, does this all make sense? And again, we talked about stationing a bit. Stationing is basically how we measure horizontal distance along the alignment. Usually throw this plus sign in there. And I really think, I don't know the true answers why that station was implemented in there. I always say I'm going to look that up and research it, never get to it. I kind of think that is so those distances are labeled this way and it just is differentiated enough so you look at that and go, okay, I know what this distance is referencing. Stationing usually begins at 0 and increases. So for example, that top example there, 0 plus 25.63 means that it's 25.63 from the beginning. The next one down, 12 plus 72.01, you see that station listed on your plans. That means that is 1,272.01 feet from the beginning of the alignment. A full station is considered 100 feet, half station 50, and a 1/4 station 25. So I also kind of, for the plus placement in your stationing, you have your foot, your tens of feet, hundreds of feet. So that goes, that plus sign you put between the hundreds and tens of feet, if you, that makes sense. Makes sense in my head. The difference in stations are the difference between the stations. So if you have two stations, you want to know the length along that alignment between two particular stations, you subtract them. That difference is your horizontal distance in between. So for example, if you wanted to find the distance between station 5 plus 0 and 13 plus 31.80, you just subtract the two, and the horizontal distance between those two, 831.80 feet. Any questions? Make sense? Could you explain it to me then? That way I know you do know it. One more time. I don't think I quite heard all of that explanation there. Okay. I guess that's one way of looking at that. Yeah, you take that, multiply it by 100. Essentially, just get rid of that plus sign. More or less is all you really need to do. I, not necessarily. It is an increment of 100 feet. Yeah, I guess. Okay, so kind of thinking of it as like a percentage is what you're doing. Okay, I guess that would work. I guess that's what the way I look at that is if you were to look at this 25 and multiply it by 100 to get rid of that, you're saying, okay, moving the plus sign over versus a decimal. Yeah. That's an interesting concept to think of this as like percentages, and it is like the engineering scale, or your engineering scale works with stations. Yeah. Okay. Okay. Good. Again, real quick, horizontal distances to the left would be considered negative or positive to the right of the alignment for your offsets. They are measured perpendicular to a tangent line and measured radial to a curved line. Elevations, vertical distances above, be considered positive, or below, considered negative, the vertical datum. As far as vertical datum goes, that makes me think of datum in the sense of, say, mean sea level, and all our elevations are in the whatever 4, 6, 800 of feet above sea level. All those are positive all the time. In the case where you might think of a positive or negative vertical distance would be for a profile. Is it above or below the existing grade? Again, I kind of just want to touch on this really quick. Talking about the offsets, you have tangent lines. Your offset is going to be perpendicular to your tangent line as such, whether it's positive or negative. This one, so we see here, this is labeled stationing is increasing as we go from left to right. This point here would be to the left. So the offset would be noted as negative. If the point was over on the right side, it would be noted as a positive offset. The radial offset, when you're talking about going through a curve, a radial line basically is any point on a curve that would extend and meet at the radius point of that curve itself. That would be a radial line. That's what the radial offset is. So if you were to start at the radius point, hit your structure or whatever this point is, and extend it straight through to the curve, that distance and that orientation would be your offset, whether it's on the inside or outside of the curve. Radial lines are good. We like those. They are far more easier to calculate than non-radial lines. Yeah, so we just kind of like that sort of thing. Radial lines are good. Roadway profile views contain two major features: gradients, vertical tangents. That would have to deal with the grade. Horizontal distances slash stations, elevations. The other major feature would be your curves. Now, from a horizontal aspect, looking from the plan view, most all of our curves are going to be simple curves. And that gets into, well, when you get into highway plans and you're traveling at higher speeds, they introduce spiral curves. However, there still is a standard simple curve component within that. Spiral curve kind of being like a parabola with no known radius to make a transition from one tangent into an actual horizontal curve, and then that parabola with no defined radius point transitioning to the outgoing tangent line. When we start talking about profiles and the curves we see in profile views, we call them vertical curves, and they are parabolic. So we have two parabolic vertical curves we deal with. They would be equal tangent or unequal tangents. I believe we have a little bit further down a better, I'll pull up a better slide that shows that a little bit more. First, I want to talk about the gradients in the grade, the horizontal distance, the elevations. Any questions on anything like that when we start talking about grade? Also, you could think of grade as slope. What's the grade of this? So between engineers, between surveyors, we like to just start naming everything a touch differently. And I'd like to look at that and go back over this one more time with this cross-section view. So if you recall from your fundamentals class, when we did the hand drafting of the contour map, rise over run equals slope. Everybody remembers that one, right? We are, let me get this down a little bit further. Yeah, I can actually point to stuff now. That slope is listed, rise over run equals slope. Multiply that slope by 100 and you have it listed as a percent. That is not uncommon when you start looking at large grading plans to see a parking lot, maybe a sheet draining at a 4% slope or 2% slope or something along those lines. Another way we like to label this, and it kind of hurts my feelings a little bit, I have to talk about the dreaded inch. And we talk about fractions of an inch. So for example, between the curb and the sidewalk here, we have a grade of 1 inch per foot. That's how that slope is labeled. That basically means you have 1 inch of rise over 1 foot of run. That's all that really means right there. So that's an easy enough to calculate what that would be as far as a percentage. Rise over run, your rise being 1 inch, your run being 12 inches. Keep in mind, before you do that, you do need to make sure your units are the same. So 1 inch per foot, we can't just, we have 1 over how many inches are in a foot? 12. 1 divided by 12, that's your grade. Multiply it by 100, that would be your percentage of your slope. Over here, within the sidewalk, we are changing to a 1/4 inch per foot, meaning 1/4 of an inch of rise divided by 1 foot of run. So does that part make sense when you see like 1 inch per foot, 1/4 inch per foot, 3/4 of an inch per foot? Does that, as far as grade goes and slope, does that make sense? Do we understand that? Okay, so once we get past the right of way, depending on whether we're in a cut fill situation, now we got a 2-to-1 slope. Now we list it as 2-to-1 instead of going whatever inch per foot, 2-to-1. For whatever reason, we label that the first number in that ratio is your run. The second number in that ratio is your rise. So essentially, 1 foot of rise per 2 feet of run. Obviously, doing the math there, take your rise over run, that would equal 0.5, multiply it by 100, that's a 50% slope. So we will label grade and slopes a little bit differently. And I kind of want to just go over that and talk about that a little bit more. Of when you see this, this is what it means. You see it labeled as a specific way, you can calc in your head, or well, don't use your calculator, but you can calculate what that means, and you're able to determine, okay, I know I'm going I can calculate my slope. I know I'm going 6 feet. What is the change in elevation? What is the rise from the back of curb to the sidewalk? We can calculate those sort of things if need be. Likewise, over here, if we want to go some distance at a 2-to-1 slope, 1 is your rise, 2 is your run. You can calculate that, and we're off and running. Any questions on grades and slopes, at least how you could potentially see them being labeled on plans? Clear? What's that? Good. Good. So maybe hopefully you'll be like, oh, okay. And if you were unsure before, hopefully this makes a little more sense to you now. So let's jump back. So that's why I wanted to kind of go back and revisit here. When you talk about gradients, vertical tangents, and grade and the slope, I just kind of want to go back to that and touch on how you could potentially see that listed on plans and what that all means. Hopefully this is legible and viewable. The colors are a little bit. So, oh, that's a good idea. Yeah, let's try that. That beat you to it. Now let's see if I hit the right light switch. Does that help? Does that help? Can you see your notes okay still? Okay, so what we have that we're looking at here would be a sample profile looking at the vertical alignment. If you can see the dashed green line and see that is noted as existing ground. So that is what the ground looks like along the proposed alignment. The purple lines would be the proposed vertical alignment. We have the gradient 1, gradient 2, and VC1, VC2, and the gradient 3. Gradient 1, gradient 2, and 3 are pretty much your vertical tangents. They will have a slope listed as a percent usually, not always, but usually on them. The VC1, VC2 are our vertical curves, our parabolas. The dashed gray lines that you see here, I think that's gray, would be as if you were to extend gradient 1, gradient 2, or gradient 2, gradient 3, where those tangent lines would intersect, like in a horizontal curve situation. I believe there's a thing that gets into a little bit more about this here, as far as breakdown of what all the parts of vertical curves. Anybody have any questions on any of this so far? Gradient 1, 2, and 3 usually will have a slope listed as a percent. The vertical curves themselves will have quite a bit of information listed on them. The beginning and end of the curve, along with the elevation, the point of vertical intersection, the station, the elevation of that point, the vertical curve length, which I will also note is a horizontal distance. And the point of these parabolas here is to make a smooth transition while you are traveling along a roadway. I'm sure a lot of people, maybe those of you who live out in more rural areas, probably know of a few hills that are notoriously fun to drive over quickly, a little hill hopping, which is not safe or good to do. But the vertical curve as a parabola is to help smooth that transition from one tangent to the other. I might be getting ahead of myself on the slides here, but I do want to mention we also have two different kinds. As you notice, with having a positive gradient coming in, a negative gradient coming out, we're going over the hill. This would be called a crest curve. We have a negative gradient coming in and a positive going out. We got this sag vertical curve. So we'll also talk about crest and sag vertical curves. Basically, crest being going over, sag under. Make sense? Gradients are defined by three elements. So you have your horizontal distance in feet or meters, stations. There's a high probability if you are going to be here in the United States, you will probably never see metric plans. However, be aware if you are doing any work in Ohio and you pull up some old right-of-way plans, I believe it was back in the 80s, this was even before my time in the surveying world, we did try to make a conversion from our US standard measurements to the metric system. So there is a possibility, particularly in Ohio, if you ever pull some old right-of-way plans that come from the 80s, there's a good possibility that they could be in metric. Other gradients, other element is your elevation, which should pretty much always be in feet. Your distances, horizontal distances, your stations should pretty much always be in feet. Your elevations would be in the same corresponding unit. And talking about grade or slope, that's going to be listed or noted on the plans as a percent grade, which we kind of just went over a little bit before, or feet per foot, inch per foot, unitless. I don't think that's unitless because we're using units to describe it. I don't know. If anybody's ever done any construction, any roofing work, maybe you've heard of pitches of roof, like a 412, 512, 612 pitch. Um, that's also like the feet per foot that we were looking over earlier, like the inch per foot that we saw on the plans. Say, for example, a 412 pitch roof would talk about 4 inches of rise over 1 foot of run. And I believe in the roofing world, that's considered a flat roof. Obviously, it's not flat. However, there's always a lot of grade on those. 612 pitch roof, you're looking at like a 50% a fairly steep roof. I do believe they make like 812s even. I'm a land surveyor for a reason. I'm not a big heights guy. I have pounded some shingles back in my day, done a little bit of roofing work with my dad when I was a kid. So dad taught me about like the 412 pitch, 512 pitch, what that meant. And just, yeah, well, that definitely got me thinking. Land surveying sounds good. Land is in the title, so I like keeping my feet on the ground. I never did like when I had to climb ladders or get up on scaffolding or get loaded up into a cherry picker to be raised up against the side of a building. Yeah, not my thing. But I've done that before too. It's okay. We survive. Feet per foot, inch per foot. You can see that listed quite a bit, like we looked at earlier in the typical section. Vertical curves, I've not quite looked at this. Percent grade, I guess they're listing as G. Your percent of grade would be your difference in elevation divided by your horizontal distance. Difference in elevation, your rise. Difference in your horizontal distances, per se, for example, like between stations or on a typical section from your center line to your edge of pavement. Difference in your elevations, your run. Rise over run equals slope. Multiply that by 100, you get your slope in a percent form. A positive G indicates an uphill grade, and a negative G indicates a downhill grade. So a G of positive 2% would mean 2 feet of rise and 100 feet of run. Just for the fun of it, we'll look back over here again real quick. This guy here. So gradient 1 is going up in this direction. It would probably be listed as a positive slope. Gradient 2, as we continue traveling left to right, would be considered a negative gradient. And gradient 3 would be considered positive of some slope. So there are two types of vertical curves. Again, we have the crest curve and sag curve. Crest curves may develop a high point, and their rate of change of grade is negative. We'll get into that when we talk about the formulas. We've already kind of touched on vertical curves and calc some by hand like way earlier in the semester. Sag curves may develop a low point. The rate of change of grade is positive. If you guys recall way back when we were calculating some of these vertical curves by hand, one of the first things we had to do was calculate that R, that rate of change of grade. From there, we can start plugging in numbers into the quadratic equation and start calculating elevations along that parabola, that vertical curve. Okay, so here we go. This is a nice example here of crest curves and sag curves. Looking from left to right, G1 is a positive slope, G2 is a negative slope, creating a crest curve, and that particular example will have a high point. I don't know if there's any other examples in this slide particularly, but you can have a crest curve that would have two positive vertical tangents. You have a G1 at some grade or some percent, and then your G2 continuing to go up, but at a smaller percentage. So you're going up a hillside and the hillside changes slope, say, for example, you go up at one grade and then you go to another grade. That would still create a crest curve, but would say does not have a high point. Same thing with a sag curve. So we have from left to right, our first gradient in is considered negative. Our other gradient coming out is positive. This could also be in the same situation. This particular example here will have a low point in it somewhere. That low point is critical because there should be a catch basin there if you're talking about a roadway, which you're going to have the sag curves in a roadway. It is possible to have a gradient coming in and a gradient that might be a little bit steeper. So again, you're kind of maybe starting to go up. You start at the bottom and you start working your way up. You're coming up and you go up. You could create a sag curve in that way. Would not have a low point. And again, the length from the beginning of the parabola to the end of the parabola, that is your horizontal length of the vertical curve. That is horizontal. The vertical curves are defined by 6 elements. The percent grade of the back tangent, the percent grade of the forward tangent, the length of the vertical curve, and again, that's a horizontal distance, the algebraic grade difference, the rate of change of grade, and the vertical offset. How exciting. I can't wait to learn more. I'm sorry, what? Oh, my bad. Take your time, please, right away. My apologies for trying to go too fast on you. After I'm done recording this lecture, however long it takes me to get it on Brightspace, I should be able to get this on today, just a little bit later. I will try to get it on as soon as possible. I will put this lecture notes on Brightspace as well with the video. Excellent. Oh, okay, yeah. We're on to this one now. Vertical curves, parabolic curves that also have several significant stations. Stations representing the horizontal distances. So we have the beginning of the vertical curve, which is typically noted as the BVC, begin vertical curve. The point of vertical intersection, where the two gradients, back gradient and forward gradient intersect, will be listed as the PVI station, point of vertical intersection. And then the end of the vertical curve, the EVC. Nothing too terribly complex there, right? Maybe? Yeah? Okay. This is a good example of looks like an equal tangent vertical curve. So you have your BVC, which is the begin of the vertical curve. That's where you go from your back tangent into the parabola. PVI, the point of vertical intersection, that is your back and forward tangents where they come and intersect. On a lot of highway plans specifically, along with a PVI, you will also be given a PVI elevation. EVC, the end of the vertical curve, so that's where you would be coming out of the parabola and begin into the tangent again, the forward tangent. G1 is the percent grade of the forward tangent. G2 is the percent grade. I'm sorry, G1 is the back tangent. I'm reading too quick. My brain's going a little quicker in my mouth. G1 percent grade of back tangent. G2 percent grade of forward tangent. L is the length of the vertical curve. Again, that's a horizontal distance. R is the rate of change of grade, and E is the vertical offset from the vertex to the midpoint of the vertical curve. How exciting is that? Personally, I think your grade in, grade out, your BVC, EVC, PVI, length and rate of change are definitely going to be the most important factors you need to be mindful of. Uh-oh. Vertical curve equations, let's get into it again. The algebraic difference, grade 2 minus grade 1. The rate of change, which is very important when we get into the equation to solve these. The rate of change is your algebraic difference divided by the vertical curve length. G2 minus G1 divided by L. Very, very important. So with this, the equation of a parabola is the quadratic equation. Y equals ax squared plus bx plus c. I know that kind of sounds a little intimidating, or at least it does to me. But when you start figuring out, okay, what is the a, b, c, what is x? X is going to be the same all the way through. I kind of feel like I need to write on the board over this or around that. I'll try to explain and let me know what you think if I should kind of rewrite this with the vertical curve elements in the equation maybe a little better. When you solve a vertical curve, you are looking for an elevation at a specific station. You know the specific station. You need to find out what's the elevation. That elevation that you're looking for is going to be y. Why not? It's going to be y because I said so. I don't know. These aren't turning out to be very funny. The a in the quadratic equation is your rate of change divided by 2. The b is your grade 1. And the c is the elevation of the vertical curve, the beginning of the vertical curve, excuse me. The elevation of the beginning of the vertical curve. So what is the x? The x and the x squared and the x here are the same value. That is the horizontal distance of the station you want to go to from the beginning of the vertical curve station. So the difference between those stations is going to be your x. Anybody have any questions on that? Does that make sense? Or do you want me to pull this up? I could kind of rewrite that a little bit to put what everything is meaning. The x is the length you're going to, or the length you're going from the beginning of your curve to whatever station you're trying to solve. That distance there, horizontal distance. So the x squared in the first part of that equation is that distance squared times your rate of change over 2. And the way I would also recommend solving that is one piece at a time. G1 times that distance you're going. That's the same distance as the x, well, not the same as x squared, but what you're squaring, that distance is the same. X is the same. You're just going to square it at the beginning and then just leave it as is in the second part. So do that little calculation there, r over 2 times your distance squared. Then jump over your G1 times your distance. Add those to your begin vertical curve elevation. Any questions? Now we have gone through and we have calculated a vertical curve. We're just kind of going through it just a touch more. I don't think we'll actually do any more calculating of them unless you guys really want to, because it was so much fun and I know you loved it. Best day ever. We love the math. Uh, yeah. I'm not going to go through the sample problem here, but again, I will put this PDF on Brightspace with the lecture, as well as I believe this week's reading is chapter 17 in your construction layout book. I think that was actually, this is 17, or yeah, I think I have it mislabeled on the syllabus. I could be wrong. I want you to read through chapter 17 of your construction layout book. That also deals with vertical curves. So again, some vertical curves will develop high points or low points depending on the sag or crest. High points are associated with crest, low points associated with sag. The location and elevation of the high and low point must be determined on plans and in the field. High and low points only occur when grades in and out change algebraic sign. So here's a little fun thing you need to do. To find the high point or low point, you need to find out, solve for x. So in this case, x is going to be the distance from the begin vertical curve station to the high point or low point station. We need to solve what station does that fall on. That distance is equal to a negative g1 divided by r. Or you could solve that as g1 times L divided by g1 minus g2. Once you have that x, that's the horizontal distance from the vertical beginning of the vertical curve to your high or low point. You can obviously add that up, and here's my station. I have that x, I'm going to plug it back into my quadratic equation. We already had the r calculated anyway. And now we can run through and calculate what the elevation would be at that high or low point. Pretty simple, pretty straightforward, right? I don't know. To me, it's not crazy difficult, just a couple equations. The quadratic equation kind of sounds a little intimidating, but I kind of feel like at the same time, even though you got fewer equations, I feel like horizontal simple curves are way easier to deal with. Either one's not really that incredibly hateful. I'm not going to go through the math and solve this. However, here would be a sample problem. Solve for the location and elevation of the low point. So here is an example. This is something you would see on a set of roadway plans. You would have the PVI station and the elevation. That is the elevation of this point, not on the proposed. If you were to assume this is an equal tangent vertical curve, from your PVI to your BVC is the same distance as from your PVI to your EVC. Well, we know the total vertical curve length. We can divide that by 2. We have that. We know our grade. So we can take this 350 divided by 2 and subtract that from our station to get our BVC station. We have that length, we know the grade, we can calculate the elevation. We could also do the same thing for the EVC here, calculate the station being that 350 divided by 2 plus your PVI station. And then also having that length and the slope, you could calculate the elevation pretty handily. So with that, what this problem's kind of going through here is, where is this low point? We need to find the station, we need to find the elevation. That goes back, first thing you want to do is solve for X on that last sheet, the station. The X that you're solving for is from the BVC to the low point. That is going to be this horizontal distance right here. We'll just go back and look at that real quick without actually crunching any numbers. That's how you would solve for the X. That's the equation you're going to use. Either or. That equation is going to solve for this horizontal distance. Then you could throw that into the quadratic equation. We know the BVC elevation. We know our X. We know our R because we've calculated that already. And we would determine what the elevation is at that low point from there. Vertical curves can be composed of two separate equal tangent vertical curves. This curve is called an unequal tangent vertical curve, composed of two tangent parabolas with differing length values. Scary, scary. Unequal tangent vertical curves are defined by 8 elements: your percent grade of your back tangent, your percent grade of your forward tangent, the percent grade of the connecting tangent, total length of vertical curve, length of first vertical curve, length of second vertical curve, the algebraic grade difference, and your vertical offset. In all honesty, from my personal experience of looking at highway plans and countless subdivision plans, roadways, plan and profiles, I would say very close to 100% of vertical curves I've ever seen on plans were all equal tangents. You probably won't ever come across an unequal. Not saying you won't, but I would say the probability is low. So we're going to just introduce this and keep moving. The unequal tangent vertical curves also have several significant stations: your PVI, your BVC, your point of compound vertical curve, so the CVC, and the EVC, the end of the vertical curve. So one extra compared to the equal tangents, you have a point of compound. So here you go. Here's a breakdown of an unequal tangent vertical curve. This here, I can't believe I'm actually going to say this, surprises me. I guess you could say this is where some calculus would come into play. So if we got any math gurus who just love calculus, looking at a function, your first derivative of a point along a parabola, your first derivative would be a slope, which is what the G3 is right here. I'm kind of more impressed that I actually remember that more than anything. But that's all the more I remember and all the further I care to dig into that one. But I'm throwing it out there for you calculus lovers. Looking at this as a function, your rate of change at that point, first derivative. Anybody have any questions on anything about vertical curves? I will have this lecture hopefully on here today. I will also have these slides with that video. Is there anything else I want to look at here? Should I add? I guess we already kind of looked at that. All right. Easy and simple to understand. So we actually went through earlier in the semester, we talked about vertical curves. We calculated the vertical curves. However, with the plan and profile of the road layout, I kind of wanted to dig in and just go through this a little bit more. We touched mostly on the horizontal concepts of the plan and profile, the plan view of roadway plans. I want to kind of go in a little bit more about the vertical component, the profile view of roadway plans.